Alright guys, so today I'm going to discuss something about secure password protocols. Um, this is basically a kind of something that's quite a bit in discussion these days, and it's already been used by a lot of different products like Apple, like Here and others. So I thought of making a video on it so that you get an understanding of what it is. So what will be talking about it. In short, it's called SRP. It simply means a secure remote password protocol. Okay. So with this protocol, basically we don't need to know the password for an individual. We just need to know, we will apply some techniques. For example, if a client is trying to authenticate itself with the server, he doesn't need to pass the password to the server. Without it, we will be able to validate if that user is really what the user is. And this is basically based on a technique or called ZKP. It's called the zero knowledge proof. So in zero knowledge proof, what we do is basically we try to validate something without knowing if that something is true or not. For example, let's say if you're standing outside a cave with a friend and the cave has two paths, let's say A and B, okay, and one of the path has a door, okay, and that door opens using a code. And now you ask your friend, do you know the code? And your friend says, yes, I know the code. But how do you know that he knows the code, right? So you might ask him, what is the code? Can you tell me? And he might not tell you. He might not want to share the code. But still you want to know if he really knows the code or not. So what you do is that basically ask him to enter into the cave, maybe twice or thrice, and randomly choose a path and come out of the other side, right? So if he repeatedly comes out of the other side, then you know that he must be knowing the code. That's how he's going to come out. So that way, I don't need to know what the code is, but I was able to validate that that person knows the code. So this is a very simplified example of a zero knowledge proof. And what we are going to discuss today is basically based on this philosophy of ZKP. So yeah, and we after going through the maths, we are also going to make implement a solution, but we are not. But that won't be a production grade solution. For implementing production grade solutions, you have certain libraries like Bouncy Castle, SRP, Java, or JPEG. Um, yeah, but we are going to write everything from scratch so that you get an understanding. That's why we are not going to use any libraries that are available. All right, so let's get started. So we have a client, oopsie, and we have a server. Cool. Now, before we get started with the SRP protocol, you should know that the first step would be for the client to register with the server. And when a client registers with the server, at that point of time, he will provide the username and password. But after that, whenever he wants to log into the server, whenever he wants to get authenticated, he would not have to provide the password. And that's the flow that we are going to see right now. So, so the client, when he's trying to authenticate with the server, so how the authentication process is going to start is the client is going to generate um, a number which is something like g to the power a and modulus n. Okay, the client is going to generate some number like this. Okay, here G and N. G is called a generator and N is a large prime number. So the client and the server would both know the value of the G and the value of N. Okay, and that's how client is going to generate this value G to the power A modulo N, right? And the server is going to do something similar. When the authentication request comes to it, it will generate a value P, which is um, so K times P plus G to the power raised to the power P modulus N. So here K is basically a random number and B is another random number. G and N are generators and the large prime numbers, as we already talked about. And what is V here? This is very important. So V here is essentially G raised to the power X modulus N, right? And what is X here? X is basically the hash value for the uh, for a salt and a password. Sorry, and the password of the user. Okay, so what happens is that user is already registered with the client. So he basically has this um, the server already has the password of the client, and we add a salt. Salt is basically a random number to it and create a hash value out of it, and that hash value is X. Now we calculate V by raising the generator. I mean, generator is raised to that this value X, and then it's made the modulo N. And this V is then used by the server to generate this value, where K here is a random number, V is the number that we just calculated, G is the generator, P is another random number, and N is a large prime number. So once these two values are generated, these two values are then shared by server and client, and we create another value out of it, which is U, which will be a hash of A and B. Like both the client has A and the client has A and the client got B from the server, and the server has A and it has B. So both of them can calculate the value of U, which is basically the hash of A and B, right? Now, let's come to the interesting part. Now the key that a client is going to generate, let's call it the S key. Okay, this this key to generate this key, what the client is going to do is that he will calculate this value B minus K times G raised to the power X. This entire thing raised to the power A plus U. This will be A plus UX. Okay. Um, so yeah, A to the power X. Yeah, A plus UX. Okay. So this is the value that this client is going to generate, and the server is going to generate something like a value as A times V raised to the power U. The entire thing is raised to the power B. Okay, and yeah, then percentage N will be there, and in this case also percentage N will be there, right? Now the interesting bit about these two values generated by the client and the server. Although the equation looks quite different, the values for S key and the S server will actually be same. Okay, so I can write it here. S key will is basically equals to S server. Okay, and if this happens, then we know that the authentication is successful, which means that the client is really the client that we are talking about. Okay, but the question that comes up here is like, how do we know that this key and this key is going to be the same? I mean, these two equations are going to generate the same value. Okay, so yeah, I mean the devil lies in the details. So let's go through this equation. The first here thing you would see here is like b minus kg to the power x. Okay, and from uh, from our from the equation that we had from the server, we know that this is nothing but this is g to the power b, right? So because b is b is kv plus g to the power b, so that if you bring this kb, and v is basically g to the power x, so if you bring like b minus k times g to the power x, then you are going to get g to the power b. So what I'm trying to say here is, like, we have, let's copy this thing here. Okay, let's, oops, sorry, let's copy this here and paste this here. So we have this equation. So from here we can say that b minus kv equals g to the power b, and because um, v is nothing but g to the power x, so we can write like b minus k g raised k times g raised to the power x is basically g to the power b. So now we know that this value here this value here b minus k, this value is g to the power b. So if you raise g to the power b then times a plus ux, then you would get something like you know the s key will be g to the power b times a plus ux, which will be equal to, which will be just what it is, g raised to the power b plus a b times a plus ux. Okay, so this is basically, this equation represents this. Now let's see what's happening on the server side. Is it also the same on the server side? So if you see on the server side, this a is basically g to the power a, and v is g to the power x. So if you replace them with their original values, then what is going to happen is g raised to the power a times uh, v is g raised to the power x, right? And the entire thing is raised to the power b. Cool. So and yeah, wait, sorry, this was g b to the power u, so this will be, oh sorry, yeah, so this will be g to the power x, because v's value is g to the power x, so this will be another raised to the power u. Yeah, now it's okay. Then so we can write this server will basically, be g raised to the power a plus ux, and the entire thing is raised to the power b. So this will be b. right? So this and this are basically the same thing, right? B times A plus UX, B times A plus UX. That is the reason why these two keys are the same. The value for these two keys will be same, and that's how we will be able to authenticate whether the user is the same or not. So in the entire process of authentication, what you saw is that the client never shared the password with the server. Only during the time of registration, it shared the password which was used to generate the value of this X. Okay, but after that, it never shared the password. And every time for authentication, we had this G and N. So you might ask like, okay, fine, but uh, there's something that's shared between by the server to the client, which is the value of the generator and the value of the large prime number. So essentially what we are doing is like we are replacing the password with some values, which is the generator and the prime number. And the answer is yes. But for any hacker, to generate the exact value of A that the client is generating in order to disguise itself as the client and try to authenticate with the server, guessing a large prime number in itself is going to be very difficult, right? And that's where this protocol essentially wins. Okay, so because the value of this N, the value of the G, is only known by the client. So the next question you might ask is, well, what if the hacker gets into the client system and gets the value of this GNN? So in that case, if I ask you, what if the client also has the SRP protocol in place? Then in that case, in order to get that prime number, he will also have to guess another prime number. So all in all, it's very difficult. It's very hard life for the hacker. So really, it's a difficult thing for a hacker to essentially get, and that's where this protocol wins, and that's why this protocol is so powerful as well as so popular, because you know because with just zero knowledge of what the password is, we can still authenticate whether the client and the server is the same, and we can authenticate that because it generates both the server and the client generates the same values for both the equations, right? Okay, so the theoretical part is done. I hope you had a good understanding of how these things work. Now let's come to the practical implication or practical implementation of this. So for that, I have created